We're starting off with exam 2 with protein structure. The first is, of course, primary, and this is protein sequencing. Know a little bit about enzyme degradation, solid state sequencing. Maybe I'll ask a question on that, multiple choice wise. The big thing will be a sequencing problem like we had in the problem set. Expect something like that as a part 2 on this exam. If I made you do it in a practice problem, expect I'm going to make you do it on the exam. All right. Yes?
We have to know what's trypsin.
Yes.
Like what kind of amino acid.
Yes. Trypsin is arginine and lysine. Chymotrypsin is phenylalanine and tyrosine. And cytosine is methionine. And of course, you have to know their codes too for those 5. Yes? What's that? Sometimes, yeah. I'm going with the most common. There is, in reality, there's sort of a loose specificity to many of these. Tryptophan sometimes, but then if you use enough, it'll cut it. Leucine, it'll cut, it gets a little more complicated. But I'm going with the most commons, first to make your life easier, and also, because it's the most generally accepted what they're going to have. Okay? All right, so expect that. Secondary, we're based on following 4 principles, which I briefly outlined here. I've asked multiple choice questions on this. I've also asked some classes to list the 4 principles and briefly define. And when I mean briefly, I mean like a sentence. Don't just say bond length constant. What does that mean? Well, that means the bonds don't grow or shrink. They're always the same between each amino acid. Yes? Oh, what the find inside rotations are?
Yeah, what you want us to know for.
Okay. So the phi on the side are the 2 rotational angles in an amino acid. This is something I never memorized, and I never thought I'd have to. And I may just end up going with the rule. If I don't have to memorize, you don't have to either. I always screw these 2 up. But really what they are, okay, I don't remember which one's which. I don't even have my notes, never mind. Don't worry about which one's which. Actually, if I looked at the diagram of a Ramachandran plot, it would tell me right off which one's which. Where is that? Where is Ramachandran? Ah, there it is. Okay. This is phi, this is psi. I always mess those up. I don't know why I can't memorize that. But they're the 2 rotational angles for every amino acid. And they can be rotated basically 360 degrees. How they like to label the rotations is -180 to +180. So there are basically 360 for each of those, basically 1 full turn. The thing is though, because of how the things such as the R group, the carbonyl, the nitrogen, all the molecules actually start bumping into each other when you twist them the wrong way, only certain regions are allowable, which means we end up with areas that are very common and areas that are hardly ever used. As a matter of fact, so you can see in this one, most of the amino acids clump near, in, or around those allowed areas. The glycines are the only ones that, because of their lack of R group, can venture outside of those allowed areas. And even then, though, if you look, let me draw. No. If you'll notice, even those glycines that are outside are fairly limited. Like this whole area down here is completely empty. Because even that's too much for glycine. It's just the way peptides bend and twist. They can't do every possible rotational pair. So this is a graph of all the rotational pairs of phis and psis. Yes?
What's the unallowed? Is glycine
glycine is the only one that can venture out of the allowed regions, yes. Everything else pretty much stays. I mean, it looks like, some of them you can see are a little bit outside, so it's not a hard boundary, but you don't really see one over here, you don't really see one there or there. They tend to group in or around those allowed regions, because any got too much variation out, we start getting a lot of steric interference, a lot of electron cloud repulsions. So you can't really just turn them all as much as you want. All right, so that's your phys and size, and that's how they're restricted. All right, let's go back to escape. Thank you. Let's go back to this. Does that answer your question?
Yes.
Okay, good. And you know what? I'll be nice, and I'm not going to make you memorize which one's phi, which one's psi, because I still can't remember myself. By next semester, I'll have it memorized. I'll make them work. If you want to memorize it, feel free, but I'm not going to make you memorize. All right. Now, the result of these rules gives us basically 3 types of secondary structures that are very common. The alpha helix, the beta sheet, which can be both parallel and anti-parallel, and the beta turn. I would also maybe expect to interpret a picture. So if you see a, where is it go? There it is. If I show you on an exam, the helix of amino acids, you're going to tell me that that's an alpha helix. If I show you the sheets, this is going to be the anti-parallel beta sheet. And if they're in the same direction, it's going to be a parallel beta sheet. So I'll be able to distinguish pictorially the difference in the different structures. And of course, this little thing up here would be a beta turn, or just a turn, however you want to say it. Okay, so have some pictorial interpretation. Yes?
Are the beta turns found on both?
Well, on parallel, not really, because if you look at a parallel, in order to go from here, you have to go all the way down here. That's too much of a beta turn. Usually we find them on the anti-parallel because you have a quick turnaround. Many times you actually find in between parallels you found helix, because it's a long enough stretch